On this slide, we talk about Kahala differentials, and in the end we will reach on the sheaf of differential forms. So first of all, we start with Kahala differentials. So start with R, a commutative K algebra, where K is a field. So this is what we fixed at the start. Then the definition. The R module of Kahala differentials or one forms. So R module of Kahala differentials or one forms. So this we write as this capital Omega with the superscript 1 R over K is the free R module generated by symbols df. So generated by symbols df, and these f lie in this R, where R is commutative K algebra, and this is modulo the relations which we have already seen in differentiation. df plus g is df plus dg, then dfg is fdg plus gdf, and dA is 0 for all A lying in K. Yeah, so all constants it is 0, A lies in K. So example will make it clear. So notice that every one form looks like this: Sama 1 to M Fi dgi. Yeah, so an example will make all these things very clear. So the first example is, we just talk over this entire K algebra, the polynomial ring over K, very easy. So this is just a free this module kx1 to xn module with basis dx1 all the way to dxn. So this is how it looks like. You have direct sum I equals to 1 to n, then k x1 x2 x3 all the way to xn, adjoin dxi to it. So for any f in k x1 to xn, you like it like this. Yeah, so this should remind you of what we did when writing the tangent plane definition. Yeah, so in tangent plane we put it equal to 0. Here we do not put it equal to 0. We just write the differential form like this. Yeah, you take partial derivatives and then you just multiply it. That is it. There is nothing else you need to do. So this is what Kahala differentials are. So you can check this thing just for monomials, because we are only talking about polynomials. So since we are only talking about polynomials, it is just sufficient to check this definition of derivatives on the monomials. So basically this df equals to partial derivative of f with respect to x1 times dx1 plus partial derivative of f with respect to x2 dx2 all the way to partial derivative of f with respect to xn times dxn. This is all you need to remember for practical purposes. So now we come to the sheaf. So for you have an affine algebraic set X. So obviously X is closed in this affine plane. So X is closed in this affine space, I should say. Yes, X is closed in affine space by definition. Now we want to talk about the coherent sheaf of one forms. So when I say coherent sheaf, it means it should be finitely generated and should look something like O of X. Yeah, so we know X is algebraic set. You immediately can think of O of X, sheaf of regular functions, and then we have some copy of it and it is finitely generated. So let us see this sheaf. How does it look like? So you have X as a affine algebraic set. Obviously it has an ideal associated with it. Now this ideal is precisely the polynomials which define X. So you have a bunch of polynomials which define X, and those polynomials are generating the ideal. Each of these GIs lies in kx1 to all the way to xn. So we want to talk about sheaf of differential forms. So you have omega 1 k x1 all the way to xn over k, and then you also have this gi is 0 and dgi is 0. Yeah, so nothing major we have done, we are just writing it as it should be. Yeah, so all these GIs and DGIs, they all have to be 0. Yeah, after all, that is what we modulo out. So let us now write it. So you write it, yeah, we are just writing it like this, and then you modulo out. Instead of GI, I will write GJ, because in the direct sum I am taking I equals to 1 to n. So the numerator we have just copied from the left hand side of the slide, and the denominator is precisely because all these polynomials vanish. Yeah, just like we modulo out from a ring, here we are modulo out from the omega 1. Till now everything is simple. Now we just modulo out with all these GJs, j equals to 1, 2, 3, 4. From kx1 to xn, you modulo out all the polynomials which define x. So if you modulo them out, what you get is O of x. That is the definition of O of x. You take kx1 to xn and modulo out all the polynomials which generate x. And only thing now remains in the denominator is dgj, and in the numerator you still have dxi. So I'm just copying the numerator out, and for the denominator dgj we will just write it like we write df on the left hand side bottom part. Yeah, so you have dgj partial derivative of gj with respect to xm, then this times dxm, and m goes from 1 to n. That is all partial derivatives. Just like instead of df, you are writing for a particular dgj, and this you have to write. I mean, for every defining polynomial of x, you have to write it. So you have to write for g1, then you have to write for g2, g3, g4, all the way to gr, all the r defining polynomials. And now you can see the sheaf is coherent because you have a direct sum in there. I equals to 1 to n, you have OX in there, and then you modulo out all the tangent planes of the polynomials which define x. So thus we can say that this omega 1 OX over k is a coherent sheaf or a coherent module. On this slide we talk about fiber of the coherent sheaf of differential forms. So you fix a point x in the space, entire space x, and we now talk about the fiber. Fiber, you know, you take the coherent sheaf and then you tensor it with the local ring at the point, modulo out the maximal ideal. Yeah, so this, you know, this part OX comma small x over mx is just the field k. Now we just plug in. First we plug in the expression for the coherent sheaf of differential forms. So we have OX dxi. Again, the space x is defined by polynomials g1, g2, g3, g4 all the way to gr. And then you modulo out the tangent planes of each of these defining polynomials. Yeah, now the only difference is that we will come to it in a minute, that we will start evaluating the partial derivatives at the point x where you define the fiber. So you modulo out the tangent planes, or I put it equal to 0, and the defining equations are J1, G1, G2, G3 all the way to GR. Tensor it again. Yeah, we have just copied the first part down. Now you first tensor OX with OX comma X. So OX with OX comma X, and then you modulo out with the maximal ideal. Yeah, so you just get K dxi. Again, why? Because OX comma X is a OX module, and you tensor it, you get OX comma X, then you modulo out the maximal ideal. What you get is a field K, and the tangent planes are there as such, again evaluated at point X. Then you have dxm equals to 0. Yeah, so what does this look like? This is nothing but the co-kernel of the map from Kr to Kn. So let us write this more explicitly. So these are just definitions of the tangent planes of the polynomials which define x. So G1, G2, G3, G4 all the way to GR define x. So let us see how this looks like. So first we write down the Jacobian matrix of all these G1, G2, G3 all the way to GR. Yeah, now we multiply it by dx1, dx2 all the way to dxn, dx1, dx2, dx3 all the way to dxn, and what you get is a series of r by 1 linear equations. You have r by n times n by 1 matrix, r by n, and then n by 1. What you get is r by 1 set of linear equations. So these are all the equations we get. So what we are trying to say is the co-kernel of this map from Kr to Kn, and we have the dual of this map, the kernel Kr to Kn. So we have kernel and its dual co-kernel, or co-kernel and its dual kernel. The kernel is nothing but the Zariski tangent space of x at point x. Yeah, so this we have already shown multiple times. Once you put it equal to 0, it becomes a tangent space, and if it is not equal to 0, it becomes the cotangent space, and the map is precisely above, and we have all the partial derivatives evaluated at the point x. So you just need to give it a thought, the way kernel and co-kernel have been defined. Now we just defined this coherent sheaf of differential forms on an open set, say UF. Yeah, so you just adjoin 1 by f to it. How does it look like? It looks like this. Yeah, for all practical purposes, you need to write it like this: OX 1 by f dxi, and then you have to modulo it out by the corresponding tangent plane, which so omega 1 x is a coherent sheaf on any algebraic set x. And if x is a smooth algebraic set, This vector bundle omega 1x is called the cotangent bundle of X. So on this slide we just record the exterior product of sheaves and then apply it to the sheaf of differential forms. After all, if we have dx and dx1, dx2 and we have to interact with each other, we have to use exterior forms. So exterior forms of sheaves, it's very standard. You take the tensor product and then you modulo out as xi, tensor xi as 0. So the rank is again R choose M, where R is the rank of the sheaf F. So F of U is a module of say rank R, then R choose M is the rank. Now let X be a smooth algebraic set over K. Then the bundle of morphisms on X is defined as the definition. This is the definition. You just take exterior product of the one forms. And we already know that tangent bundle is the dual of this omega 1 bundle. This we talked about on the previous slide. We talked about co-kernel and kernel map as being dual of each other. Now we talk about this. What is canonical bundle of X? So this will come in Riemann rock. One of the forms of Riemann rock involves this canonical bundle of X. So this is nothing but this sheaf of differential forms, exterior product, you take it, n, where n is nothing but the dimension of the algebraic set X. So the rank of this would be n choose n, which is 1. So since the rank is 1, Kx is nothing but a line bundle.